We know on Earth, all life, from the tiniest microbes to the largest elephant, needs liquid water. But that may not be the only solvent that is possible for life. And so we do need to be looking for life as we do not know it, life that might exist, for example, on Saturn's moon Titan. If we find life there, that is definitely going to be life as we do not know it.
Welcome to Closer to Truth. I'm speaking with Dr. Aomawa Shields about her engrossing new book, Life on Other Planets, a memoir of finding my place in the universe. It's about astrobiology, science and our culture, gender and race, and personal fulfillment. Welcome, Aomawa. A quick opening question. What's the likelihood of discovering life on other planets during your career?
Well, first of all, thank you so much, Robert, for having me here. I'm really excited to talk more. And I would have said, if you'd asked me this question 5, 10 years ago, I would have said it's highly unlikely that we will find evidence or at least answer that question, are we alone in the universe, within my lifetime. I'm not fully convinced that unlikely is what I would say today. I think today I'd say that it's possible. And if not in my lifetime, then in my daughter's. Our instrumentation is becoming more and more advanced, and we're actually surprising ourselves in terms of what we're able to discern from things like James Webb. So I think that literally the sky is the limit at this point. Or the sky is not the limit.
Good metaphor. I just give me a 1 to 10 likelihood. You and I are scientific backgrounds who are quantitative. I'm gonna give you trouble. So just give me a 1 to 10 likelihood.
I can't do that. As scientists, we need to have evidence to be able to make statistical arguments.
I can't do it.
If we find out tomorrow, then someone's going to say, "Aha! She said it was 70% likelihood that we'd find out." So yeah, we need more evidence to be able to do that.
Fair enough. So let me ask the question this way, more specifically. What kind of atmospheric signatures would be considered proof at different levels of confidence? It's about sigma 4, 5, 6, and all of that. So what would be an atmospheric signature that would give you that confidence level?
So a lot of the astrobiologists in our community are really aimed at determining this recipe of biosignatures. These are these biologically generated global impacts to a planet's atmosphere or surface that we could observe remotely, like from space. But we're still figuring out what that recipe actually is. It can't just be oxygen, even though we know that much of life on Earth requires oxygen. Not all life requires oxygen, and there are abiotic sources of oxygen. Volcanoes emit CO2, outgas CO2, and that gets split apart by light in a process called photolysis, and that O2 could be picked up, and we would think there is life there, but it could be what we call a false positive. So people are thinking about things like O2 in combination with methane, because those two gases rarely coexist without something replenishing, and O3, ozone, along with oxygen and methane, could also be helpful. If you've got a lot of O2 in the atmosphere, that O2 is around to split apart light. But again, there's still a lot of ways that we could create that signature that might not necessarily mean there's life there. I think what I've heard recently that's really important is this idea of disequilibrium. So life is not an equilibrium environment. It doesn't produce an equilibrium environment. So when there's life present, that usually means that there's a lot that's in disequilibrium, a lot of gases that are being emitted, excreted, and things that are being canceled out. And so if we look for that disequilibrium signature, that is a very good indicator that there's something on the surface that's...
Would that mean a dynamic picture over time, that you have to see these changes over some periodicity.
Absolutely. So it's not like we would just take a snapshot or take one spectrum and that would be able to tell us unequivocally. We would need to look at this over time. So
Uh,
so there, but those astrobiologists who are specializing in biosignature detection, people like Vicki Meadows and the Virtual Planet Laboratory are really over the next 5 to 10 years working hard to come up with this recipe of different biosignature gases that would tell us unequivocally that life is there.
and we always have to put the qualification life as we know it, right?
Absolutely. Yeah, because liquid water is what we're looking for. So what I do as an astrobiologist is use computer models to be able to determine which of these planets that we've discovered might have the best chance of hosting habitable conditions. And by habitable, we mean capable of supporting a climate conducive to the long-term presence of surface liquid water. Because we know on Earth, all life, from the tiniest microbes to the largest elephant, needs liquid water. But that may not be the only solvent that is possible for life. And so we do need to be looking for life as we do not know it, life that might exist, for example, on Saturn's moon Titan. If we find life there, that is definitely going to be life as we do not know it, because that liquid is liquid ethane and methane. It's not water. So we need to be doing both.
Good. Uh, Before I give your bio, we always like to do that more formally. Give me a little bit of an overview of the book, because it so wonderfully weaves together your personal stories, your triumphs, your difficulties, your challenges with the science in a very organic way. So normally when I talk to authors, there's a very clean, linear approach. Yours is nicely chronological, but it interweaves the personal. So give me a flavor of how you wrote the book, why you wrote the book, and it's certainly a memoir, but it's a deeply personal one.
Thank you. I have been telling this story, I realize, in many ways for a long time in short segments. Like I would write essays that talked a bit about my career path. I would write poems, but writing the book, it was like it all came together. And I started it in August of 2020, and I wanted to tell my story because it is so non-traditional and, as you mentioned, very non-linear. Yes, it is chronological, but it's like in terms of my career path, there is nothing linear about it. I knew I had this unusual background in that I loved both astronomy and I loved acting. And I now know that they're not as disparate as I once believed, or as people that I would tell would often tell me, like, why? How did this happen? How do you put those two together? And for so long I was trying to figure out how to do that. And I wanted other people to know, because I know that I'm not as rare as I once thought I was. In the book, I call myself a rare magical unicorn. But I have since been contacted by people from all over the world who have these different loves, these different interests, and they cross disciplines and they're not sure how to put them together. And so I wanted people to know that this is one example of someone who's done life a little bit differently and found meaning and fulfillment, so that they would feel a little bit less alone. And it's also written for people who have left a dream behind and they're not sure how to manifest it in their life. They're afraid it's too late, because I'm someone who came back to astronomy much later in life compared to my peers. I had a child much later in life compared to most people. And there's a lot that I did. At one point I called myself a late bloomer, because a lot of the stuff I've done in my life, I've done a little bit later than the norm.
And a lot of stuff you did earlier than the norm too. So norm is nothing, is not an adjective among the many that I would apply to you.
And that's the thing. I wanted people to know that just because they haven't seen someone doing what they want to do, doesn't mean that they can't do it. Like, I internalized for a long time that, oh, no one's putting science and art together the way I want to. Oh, no one's doing astronomy and looking like I do. And I thought that meant that I shouldn't do it. And I now know, of course, that that's not true. But many people out there may still wonder if they can do something if they haven't seen someone else do it. And so I wanted to encourage people to be their own role model. So that's a lot of the message in the book as well.
That's a terrific book. I do want to give of your bio, but first, we have to tell the story of your most musical first name. And as you said in the book, which I had come to the book initially, I first thought it was African for obvious reasons. Then the last four letters sounded very Japanese, and then the whole thing sort of sounded Hawaiian, like that visitor that we had from outside the solar system, that the cigar shape.
Yes,
That,
mua mua.
I couldn't pronounce that. So yeah. So but all those are wrong. So tell me quickly the musical story of your wonderful name.
Yes, as people will read in the book, my parents are musicians. They're still quite active, and I'm someone who gets to say that they had a band in college, and I can literally say the band got back together again, and they have toured really during while I was writing the book and finishing up the book. They were touring in Europe. So when I was, in the womb, they were playing music. My mother was playing flute and dancing. My father played saxophone, and then they learned dozens of other instruments, both African instruments and other instruments. And they created a song, a chant, and named me after the chant. And it's now I can actually do the chant. In the book, I have to just write it, and I have to
Yeah.
say, use your imagination. But it was like, Aomawa, Aomawa Lalahie, Aomawa, because Lalahie is my middle name. And so that's where they created the chant out of vowel sound. So it has no origin in any country or ethnicity. It's from vowel sounds, and they made this chant and then named me after the chant,
What
the first and the second.
it's a wonderful story, and it's very much proleptic in the sense that it gives a an early indication of your incredibly diverse and interesting life. So
You want to know the meaning of it?
yeah, sure.
So they gave me a meaning. They gave the name its own meaning, which is spiritual strength,
Oh
which, as
wow.
you find in the book, is also quite relevant and appropriate.
Right, and we'll talk about that near the end as well. So let me give the official bio. Dr. Aomawa Shields is an astronomer, an astrobiologist, the Clare Boothe Luce Associate Professor in the Department of Physics and Astronomy at the University of California, Irvine, and a classically trained actor. She is the recipient of the NSF CAREER Award and the NASA Habitable Worlds and Exoplanets Research Program grants, among others. And she's also active in science communication and outreach, especially encouraging self-esteem and teaching about astronomy, which combines her career in both in astronomy, as she said, and her training in theater. Now, the thing that attracted me most and most astounded me of all the things that you've done, because I've been in science and have taken different routes, is that there was this 11-year hiatus in your science world when you went into acting and other artistic endeavors, and then to go back to a PhD program. Now, if you were doing that in medieval literature, that'd be hard but easy. But to do it in STEM, science, technology, engineering, mathematics, that is a hell of a challenge. So tell me about that.
Thank you. Yes, when I returned, there had been 11 years, as you say, and I call it a solar cycle. That's the chapter in the book, because our solar cycle is 11 years long. And yes, it was overwhelming to come back and essentially start again. I had forgotten so much. Over a decade ago was the last time I had been in astronomy. So I had to work really hard. I mean, that's really what it comes down to. And I had a lot of imposter thoughts that I had certainly justifiable reasons for feeling those. But I think what it came down to was knowing that because it wasn't so fresh in my mind and the way that it was for my peers, that took a lot of extra study for me to bring it all back, and in some cases learn things really for the first time, it felt like.
Yeah. Well, it took guts as well as smarts to do that. That significantly impressed me. I would really fear going back into the sciences, even though I have followed it very deeply. There's one thing to know it on the surface, and another thing to do problem sets, as we know.
Yep.
That's a term that I think you and I would both feel terror when we hear that very simple term.
Yes. That's why acting grad school at first felt like playtime, because there were no problem sets, and I was like, oh my god! And I actually get to go to school and not do problem sets. What's going on? But I learned later on that it wasn't all play.
All right, let's go into astrobiology and your core research. I want to get into a lot of other questions, but I do want to have a good section on your core research, climate on exoplanets. Your research focuses on exploring the climates and habitability of small Earth-like exoplanets orbiting generally low-mass stars, which we'll talk about, using data from observatories, including NASA's Kepler spacecraft, which was an amazing situation. So give me a sense of how do you take climate models that are designed for modeling the climate and weather patterns on Earth and adapt those to exoplanets?
I'm so glad you asked this question. So we're using climate models that have historically been employed to predict climate and weather patterns on the Earth. So they were used to predict the impact of anthropogenic, that means human-made, carbon dioxide-induced climate change into the 2100s. But what we're doing is changing these models ever so slightly to allow us to predict the climate and weather patterns on other planets orbiting other stars. So what we can do is change the spectrum of the host star. And what that means is, every star has its own distribution of light and across different wavelengths. The sun is a type of star that we call a G star, and that's the reason why it shines the way it does, the reason why it looks like the way that it does in the sky, is because of the type, that its temperature and the type of energy that it emits across certain wavelengths. Different stars in the galaxy have different properties in that way, and the sun is actually not the most common type of star. Actually, these low mass, cooler, redder stars are 75% of all stars in the galaxy.
That's amazing. That's the M dwarf star.
So those M dwarf stars, red dwarf stars. So, and as an example, we can change the distribution of spectral energy to have that host star be an M dwarf star instead of a sun-like star. And that, just changing that knob, changes everything about what the climate's going to be like on a planet, given things that...
Let's understand all the different knobs that you work with. I mean, factors like, obviously, the host star, its spectrum, the distance from the star, the eccentricity or obliquity of the orbits, the atmosphere, rate of rotation, density. I mean, I'm just throwing out words. What are some of the core knobs that you can manipulate to get different results?
Yeah, well, you just named a fair amount of them, like the spectrum of the star, the shape of the orbit, the eccentricity, the obliquity, how tilted the axis is, the atmospheric composition. I mean, this is one of the major knobs that we turn because we can't know yet. We don't know what is in the atmospheres of these small Earth-sized planets. We've gotten to the point where our instrumentation is sensitive enough to detect Earth-sized planets, even with James Webb, which I believe was surprising. And now we want to know what's in their atmospheres. And since we don't, my team's work is critical because we're filling in the gaps between what we do know observationally, which might be size of the planet, maybe its mass, maybe something about the shape of its orbit, but there's not a whole lot we can constrain yet with observations. And we need to know which planets have the best chance of being habitable so we can follow up on those with next generation instrumentation to see what is in their atmospheres and to be able to detect these things called biosignatures. So we can say, okay, let's see if we give it this kind of atmosphere, if we give it an Earth-like atmosphere, this planet, could it be habitable? And we can run the model and see what that surface temperature pattern looks like, how much of the surface is warm enough for surface liquid water. We also can change things like beyond the orbit, we can change the obliquity, we can change the type of surface. So we don't know things like what's on the surface of this planet. Often we assume that the planet is covered in ocean because that makes our models simpler and they sort of run faster if we give them a slab ocean, which is 50 meters deep and has no ocean heat transport. That's not realistic, but it allows a model to take a week or two to reach equilibrium instead of months. And then we can say, okay, let's see if we give it a fully dynamic ocean that's 4,000 meters deep, and we have the time to see how that plays out, then we can determine what the habitability would be like then. But there might be surface compositions other than ocean, just like our planet. We have so many different surface types: desert, calcite, granite, and ocean. And we don't know what the surfaces might be like on these planets. So we say, okay, if some part of its surface is land, and what kind of land. And that's sort of my specialty, is looking at how surface compositions can interact with starlight and how that interaction affects climate. So there's a lot of knobs that we can turn, ultimately to allow us to determine how habitable these planets are as a function of these factors that are currently unconstrained.
So let's go back to, I mean, that's fascinating and critical. But let's go back to what is the raw data that you're actually working with, because planetary detection, I mean, most people who watch this know what this is, but just to review, there are a couple of different techniques that are used for planetary detection in terms of ambient light as the planet crosses the stars as we look at it, or the radial movement of the star based on gravitation. And then the capacity to know the atmosphere we're trying to do. And I'd like to know what the state of the art is, because as the planet just transits the star and the starlight before the planet hits the star, you can see through that, potentially through the atmosphere, and get a spectrographic analysis. So how much of that data are you using, and is it robust enough yet?
So we do use observational data whenever we have it. And for the most part, the data that we use includes radius information and mass information. If for the Earth-sized planets, we don't have the kind of atmospheric composition information that we need and want to have. This process of transit transmission spectroscopy that you're talking about is certainly the pathway to getting that information. But we can do that. We can use that and allow us to determine and that allows us to determine what's in the atmospheres of these planets if they're larger on the order of Jupiter class, maybe a little bit smaller. But we're working towards being able to do that, and hopefully we'll be able to. Like, I know that there's James Webb observations planned for an Earth-sized planet that was found with James Webb or confirmed with James Webb in January. They're looking to go back and take data and hope to get atmospheric compositional data. But largely it's mass, radius, and like distance. So the amount of light that the planet gets from the star, that translates to, an orbital distance. We know how far away the planet is from its star, and we know how luminous this star is, the host star, and so that can allow us to determine how much light is hitting that planet's surface per square meter, and we can put that information into the climate model.
Yeah, that's a really important point, and I thought an interesting point you make in the book is that because the composition of the spectrum of different stars and the composition of the light differs, it will have a different effect. And you use ice as an example, where ice is not just this purely white thing that we see during the wintertime, but with different star spectrum, it will have different grays or black colors, which will dramatically affect the albedo and the reflection and the climate change. So it's fascinating, but really complicated.
It is. I mean, this was how I found my dissertation topic. As a grad student, one of the things you want most is to find that thing that you will be willing to work on and want to work on for the next 5 years, or at least 3 to 4 years once you pass your qualifying exam. And I walked in, as I say in the book, I walked into a journal club talk, and a senior grad student was giving a talk on a paper by Manoj Joshi and Rob Haberle. And it was a suppositional paper that was kind of proposing that because water ice has this property such that it is very absorptive of longer, redder wavelength light, which is the bulk of the light that comes out of these M dwarf stars, it's emitted by them. and is reflective of visible and UV light, and the sun, over 50% of the sun's light is visible light, that could influence how the climate of planets orbiting these M dwarf stars might be. So like and might be affected. The M dwarf planets could have less ice on their surfaces because that ice would absorb a lot of the red and infrared light from the M dwarfs. And so with that small principle, I basically created an entire dissertation topic around the effect of star-planet interactions on planetary climate. And of course, that starlight is also being absorbed and or reflected by whatever's in the atmosphere of the planet. But what we were able to show, and what I showed as part of my PhD, was that the surface matters. Many of us in exoplanets have operated under the assumption that it doesn't really matter what's on the surface because we can't get that sensitive enough to tell what's on the surface of an exoplanet orbiting trillions of miles away.
Right.
At this point, at best we would hope to be able to see what's in the atmosphere, but like forget about the surface. And what we showed in our climate models was that the climate is sensitive to the surface, and it's sensitive to the surface well into the habitable zone, and well, like even towards the outer edge, the climate is still sensitive to the surface. Once you get towards the outer edge of the habitable zone, assuming that your planet has a carbon and silicate cycle like our planet does, whereas temperatures get down, there's less precipitation, and volcanoes outgas CO2 to regulate the temperature. If that process operates on exoplanets, which we don't know that it does, but we're assuming that it does when we calculate the habitable zone, then there could be so much CO2 in the atmosphere farther out that you eventually would mask the planet's sensitivity to the surface, the climate sensitivity. But there's this very large swath of space within the habitable zone where it does very much does matter what's on the surface, because these ices, and we've gone on to show that different types of land have this range of optical and infrared properties, such that the surface matters in climate studies.
Absolutely fascinating. Let me try to get some sense of the data that we're working with, and I like to always keep checking the number of confirmed exoplanets. And this is an interesting thing for Closer to Truth, because when we started 27 years ago, the number was really small. It was like 100 or something, and you can see over the years how it has grown. And TV shows that we have, you can date them when somebody mentions the number of exoplanets.
Yes,
And so
yes.
I note in your book you have 4,300, and the book was published last year. I mean, it was written last year and finalized. And I checked, as of July 12th, 2023, there are 5,470 confirmed exoplanets in 4,069 planetary systems, with 924 systems having more than one planet. So that's the latest data that I've seen. And based upon your tracking of this, is there any way you can forecast or sense what the technology is giving us in terms of how that number will develop in the future? I mean, to project it linearly would not make any sense. I mean, you must have do you have a sense of where that number is going?
I do. So the reason why this number, if you look at a graph, and they have these graphs now in the NASA's exoplanets websites, you can see that it is a nearly exponential increase in the number of planets that were discovered since the early, the mid to late 1990s. Well, the mid 1990s is when we discovered the first planet orbiting a main sequence star other than the sun. And then we had, like, as you say, we went from hundreds to thousands, and it shot up really quickly between 2009, from 2009 and the last, 10 years. And that's largely due to NASA's Kepler mission, which operated for almost a decade and found, I think, close to 3,000 confirmed planets. So it took us just way up in that number. But the thing is that Kepler was only staring at one patch of sky for almost those full 10 years. A little bit less, because eventually it lost a couple reaction wheels and it had to be repurposed, and it was looking at the ecliptic. But for the bulk of those 10 years, it was looking at one patch of sky, towards the constellation Cygnus and taking pictures looking for the dips in starlight caused by transiting planets. Now we have the successor to Kepler, which is the Transiting Exoplanet Survey Satellite, TESS, and it is not only looking at one patch of sky, it is an all-sky survey. And it's looking at for planets around stars in the nearby solar neighborhood. And I'm really excited about that because even though I worked on a particular planet discovered by Kepler 62F, which is very close to my heart, that planet was 1,200 light years away. And so we didn't have much of a hope of following up on that planet with missions like James Webb or future mission concepts because it's so far away. We want to be able to follow up to see if there's anything in the planet's atmosphere that could tell us that life's there. With these planets that TESS is finding, we're going to be able to follow up on them much more easily because they're in the nearby solar neighborhood. They're in our proverbial backyard. And because TESS is an all-sky survey, I predict we're going to be able to double this number within a couple years. No, I made a prediction, so we'll see if that's right. And it's just going to keep going. It's going to keep going and going. And I think that, that 5,470 number is impressive. And I think it's even more impressive when we realize that that's from surveying the tiniest fraction of the sky. Remember, we've got over 100 billion stars within our own galaxy alone and hundreds of billions of galaxies within the observable universe. So I tell my students that's 10 to the 22 stars minimum, and just about every star has a planet around it. So just think about
so that to me is a fascinating analysis. Let's talk about that in terms of the order of magnitude. So if we have the latest estimate is like 2 trillion galaxies, which has a number that has been growing. It used to be 100 billion. But in the last several years, I think the latest is 2 trillion. We can eliminate the 2 in these orders of magnitude. So a trillion is 10 to the 12th, and average stars per galaxy take 100 billion, as you said, was the traditional Milky Way. Now the Milky Way, they estimate 400 billion. A lot of them are small, and there's a lot of smaller galaxies. So take 100 billion. So that's 10 to the 11th. So 10 to the 12 times 10 to the 11th. So that's 10 to the 23rd. So the estimates I've heard are between 10 to the 22nd to 10 to the 24th. That's the range of estimates of the number of stars. Yeah. Now that was the first. Now the next question, which you're starting to answer, which is the fascinating one that we had no idea of before, is the average number of planets per star. Mm-hmm. And nobody had any estimate that you could make reliably just a few years ago. That's right. But now you're saying, and that's one of my questions, what is the best guess for the average number of planets per star? And average is saying is the mean, and so that we could get an estimate of the number of planets.
You're asking a theorist an observer question. Let's just be clear. But I will, within my realm of understanding, based on papers I've read and colleagues who are observers, is that just about every star has a planet around it. Now that doesn't mean that the planets that are orbiting these stars are all within the habitable zone.
No, of course. That's a separate question.
But there is if we go back to Courtney Dressing and Dave Charbonneau's work of the last 5 to 10 years, they were able to show, and there have been some other studies that have maybe increased this number a bit. Eric Pitagura's work, we've looked at the number of around 20%. 20% of those planets are in the habitable zone. So 20% of all stars have a planet, or of the planets that are orbiting the stars are in the actual habitable zone. And so that is still, and it could be 25%, 20%, depends on.
Oh, that's an important number.
Yeah.
But let's go to the earlier number, the average number of planets per star, because that seems to be growing. I mean, some estimates I've just looked up would give something like 10 to the 25th a number of planets, which would mean there's an average of maybe 10 per star. I mean, what's a planet? We can go back to the Pluto argument and what's a planet and what's not a planet. So we get all that. But another thing that came up, and I'd like to get your thought on it, that in addition to the planets orbiting stars, there may be even a much larger number of starless planets that are sort of wandering around without a parent.
Well, it makes me think of, I don't know if you've ever read the science fiction story by Fritz Leiber called A Pail of Air. I talk about it in the book.
I didn't, but I read it in your book, and it was a great story, and that's what I want you to tell.
Yes, so this idea that rogue planets exist. So in Fritz Leiber's story, the sun has lost its star, and therefore all of the atmosphere, without the heat from the star, from the sun, the atmosphere condenses out onto the surface. And I love that Fritz Leiber's his narrative is based in a lot of science, that they condense according to their own condensation temperatures. Each gas has its own condensation temperatures based on its individual properties. And so like you have certain gases that are condensing on top of others in line with their condensation temperature. And this one family still lives on the planet, and they think that they're alone, and they live deep underground where it's still warm. But every day someone has to go up to the surface and fetch a pail of air from the surface, which is in its condensed form, so it's like snow basically. But they fetch the pail of oxygen, condensed oxygen snow. They put it in the pail. They go back down. They're like packed in all these insulation suits to not freeze when they go up to the surface. Then they go back down and they put that air over the fire and let it sublimate back into the atmosphere, and then they're able to breathe.
Yeah, amazing.
And it's just a wonderful story. It's a short story, and it's exciting and compelling.
Yeah, look, it is terrific, and it really focuses on your core interest in the nature of water and ice on different planets and along stars, and you talk about the importance of snowball Earth in understanding climate and therefore projecting that into exoplanets.
Well, this also leads me to think about, I absolutely love to use observational data when we have it available for planets. And of course, that's the most interesting, I think, in the public's eye, because if we have an actual planet out there, my team can help determine whether that planet could be habitable if it has the conditions. But there's another side of the work that where it all started for me, which is not necessarily using data, but turning knobs, creating hypothetical planets in my mind, and then putting that into a climate model to determine what classes of planets around what types of stars we would want to prioritize. So this work is important because there's, as we talked about, there's so many stars out there, and there's many different spectral classes of stars. And there's a discussion about what type of star should we really look to for whether planets are habitable. So people have thought it should be sun-like stars that we focus on. Others think it should be these M dwarfs because they are so numerous. And being able to, and each stellar environment is unique. We know that M dwarfs have a very unique stellar environment, very different from sun-like environments because of how long they live, and there's just a lot that's very characteristic of the M dwarf stellar environment. And my team has been able to create these planets put them around different stars, and that allows us to really quantify the effects of a particular stellar environment on certain planetary systems. And we've done that when you mentioned the rogue planet thing. We've been able to think about M dwarf planets that might be synchronously rotating. And that means that they've got one perpetual day side that's always facing the star, and the other side, it's always nighttime. And there's been concern in general that those types of planets may not be able to host life. It could be searingly hot on the day side, too hot for life. And on the night side, so cold that the atmosphere freezes out, like it did in the Fritz Leiber story. And we wanted to ask the question, is there a scenario where, yes, it's too hot on the day side, it's too cold on the night side, and it's only habitable along the terminator, that dividing line between day and night? And we wanted to see if these planets could exist out in space. And so to do that, we had to create them. And we were able to, and it took a long time, and my postdoc, Anna Lobo, who's fantastic, and anyone listening should hire her, try to steal her away from me. And she was able to show that, yes, you could have a scenario. And it's actually harder than you think to create that scenario, because it can get so hot on the day side that you start a runaway greenhouse, which is what we think that Venus succumbed to, our planet. And then basically the whole planet is just too hot. And so that wouldn't be the scenario that we want, because we were looking for, again, that strip, that Terminator dividing line where it's just right. And then another scenario, another case is, if it's too cold, that actually could overshadow the whole planet. And so finding a scenario in which we do have too hot on one side, too cold on the other side, and just right in the center took some time, but we were able to create it, and we were able to show that it's much more plausible for water limited planets. If there's a lot of water on a planet, then that runaway greenhouse situation is more likely. But for water limitation, and we were able to, our paper is called, Terminator Habitable, the case for water limited planets, M-dwarf planets. So we're saying that, yes, some water is of course necessary, assuming we're talking about life as we know it, but not too much. And that might actually be more, be more conducive. And we might want to look for planets that have less water out in space. And we think that M-dwarf planets in general tend to form with fewer water, fewer amounts of water, because of their small protostellar disk material. There's just less water, less stuff.
So roughly how wide is this Terminator zone, this habitable zone of this planet that always keeps the same face to the star?
Yeah, so our resolution within the model certainly dictates that. I think we have a resolution that would allow us to resolve maybe hundreds of meters or so. And so this is a pretty narrow strip so far.
Yeah. Look, that makes sense. I loved your statement in the book, because your book is so refreshingly self-critical, self-deprecating, wondering this, wondering that, and you have a very personal feel. So I feel like, you and I went to high school together. I've known you your whole life, just reading the book. But you have this one statement which stands out from all the others, which is a very aggressive, affirmative, highly confident statement. It stood out because it's very unusual in the book, and that says, very authoritatively, I can tell you for any given planet whether there's a snowball's chance in hell of supporting life as we know it. I love that statement.
Thank you. I feel that way now after a long time in this field, and knowing my models and knowing what they're capable of. And so it felt empowering to write that.
Good. We'd love to talk more about the details of the of your science, but I think we have a good feel for it. What I'd love to do now is just get your philosophical views, having been in the field and dealing with astrobiology, of some of the really big questions that are impossible to answer. So, but I'd just like to get your feel for what some of these are. And so when we look at the big picture of astrobiology and our universe, I like to think that if you compile what people have said, there are a number of key transitions that need to occur or need not occur. But the traditions, these transitions, as I see them, are the following. I'd just like to get your feeling on this analysis. The first one is from non-life to life, in any simplest form. Second is from simple life, whatever that may mean, normally single cellular life, to complex multicellular life. We know on Earth that process was a very long one. Life started early, maybe 3.5 billion years ago, but the process of going to multicellular took a healthy percentage of that time, it measured in billions of years. Then from complex life to anything approaching the nature of intelligence, sentience, consciousness. It's a third transition. Then we can go from consciousness to a civilization, and from civilizations and culture to technology as the kind of transitions. So as you look at these big overall picture, well, What are your feelings about these different potential transitions? We know only one thing for sure, that we on Earth are a single data point that have gone through all five.
That's true. Well, I was always fascinated when I got back to grad school the second time around by this period of time during which it's the Neo-Proterozoic. So that's like 800, 600 million years ago, when several of these snowball Earth episodes occurred, when there's paleomagnetic and geologic evidence to show that the Earth was covered in ice from pole to pole. And it wasn't just that they occurred that surprised me and fascinated me, but that life survived, because life, as you say, it had already been around for billions of years at that point, and that even photosynthetic life survived. And I thought, how is this possible? If there was like a kilometer of ice, how could photosynthetic life have survived? And maybe the ice wasn't a kilometer thick, and maybe there were like isolated refugia. We don't know. But one thing that I've learned from this whole field is that life finds a way, and that everywhere on our planet there's life. These boreholes in the depths of South Africa, and the frigid temperatures in Antarctica, and these little frost flowers, and extremely acidic environments and desiccated environments, and life is there. And so that's exciting to me when I think about the prospects for life elsewhere. But I also, your question about, or I guess the sequence of life that you reminded us all of right now, is it leads me to think that there might be different ways that I could imagine life carrying out its different evolutionary processes. Do we know that life has to eventually lead to advanced technology? This is a question that comes up in my Life in the Universe class that I write about in the book. We talk about Fermi's paradox, this whole idea that if there's so many stars out there and almost every star has a planet, then where are they? Where is that extraterrestrial life? Why hasn't it made contact? And there are several proposed hypotheses in answer to this paradox. And one of them is, that perhaps that life out there has already blown itself up because it's reached such a technologically advanced stage that they didn't know how to handle that technology. There's like the zoo hypothesis that basically they're here and they're watching us and we don't know it, or the sentinel hypothesis is one of those two. There's many hypotheses, but I think it's important to realize that technology is not the only indicator of advanced life. And we can think about different philosophies here on our planet, the Buddhist monks who live on the top of mountains, and we might consider them highly intelligent. I certainly would. And one of the tenets, I think, of their philosophy is that they're sort of the non-doing, and the not necessarily feeling called to use that intelligence in service to advancing technology. Might there be life elsewhere that has a similar philosophy, that has reached a certain level of intelligence and yet has not identified the need to spread themselves beyond their own environment? These are, I think, possibilities that we must consider as well.
All true, and I think there are several dozen, 50 or more answers to Fermi's paradox. But my answer to all of them, which I'll give to you, is that every one of those 50 and every one you said, can be true millions of times. But you really only need one in our galaxy that is different, that doesn't fit those, because within several dozen million years, which is an eye blink in universal history, through technology, through self-replicating so-called von Neumann probes, you can run a quick model and show that those probes can fill a galaxy in 20, 30 million years, based on technology that's not wildly ahead of what we can do today. And so that's the real Fermi paradox, that it's not that any of the answers are wrong, but it is that there cannot be any exception to those. And that I find very troubling.
You're right that all we need is one. We only need one example of a civilization on another planet orbiting another star that exists and has allowed its existence to be known, either through contacting us, or us determining that life is there through our observations. And I actually find that extremely hope-inducing, because we only have been capable of sending signals out for since the 1930s, signals that could actually be broadcasting.
Yeah, I love Lucy is about 70 light years away from us, and if you look at a big picture of the Milky Way, 70 light years you can't even see.
That's
It's
right.
it's so small.
Yeah, so like it may just have been it may just be the case that we haven't, our signals have only propagated so far, and our planet has been around for 4.5 billion years. Or the lifetime of our star is 10 billion years, so we're about halfway through our star's lifetime. These M dwarfs have lifetimes of hundreds of billions, and in some cases trillions of years. So that's another advantage. They offer long time scales for both planetary and biological evolution. So life, if present somewhere else, might have not gotten to the stage yet where it's able to send its own signals. But like you say, it only takes one, and hopefully that civilization's ability to broadcast signals or somehow make its presence known will align with our current lifetime.
You say in the book that you are not religious, but you are spiritual. Tell me what that means.
So I believe that there is a gap between what we can ever hope to fully understand and know as scientists, and as philosophers, and what actually the truth really is, and what exists. And so an example of this is the Big Bang. Although I know much of cosmology is currently in flux, of course, because of some of the James Webb discoveries and observations, but I'm operating under what I've learned over the course of my career so far, and this idea that we know that the universe is about 14 billion years old, and M dwarfs have lifetimes that are hundreds of billions of years old, in some cases trillions. We know that the Big Bang happened at 10 to the minus 34 seconds or something like that, and that created the universe from nothing. So everything was created from nothing. But what caused everything to be created from nothing at that 10 to the minus 34 seconds? I don't know. I certainly don't know, and I don't know that any cosmologist can answer that question yet. What happened and why? Like, what caused that to happen then and why? And that's one example of, there's a space between what we can know and what exists. And I think that's where some power greater than all of us resides. And I've never felt that that's in conflict with my practice of the scientific method. I certainly will tell you, science tells us that the Earth is 4.5 billion years and old, and all of these. I'm grounded in science. However, there's a lot that I think science is also unable to explain, and that's where spirituality comes in for me. And I know that actually I have a quote right here. Carl Sagan wrote in The Demon Haunted World, "Science is not only compatible with spirituality, it is a profound source of spirituality. When we recognize our place in an immensity of light years and in the passage of ages, when we grasp the intricacy, beauty, and subtlety of life, then that soaring feeling, that sense of elation and humility combined, is surely spiritual." And I could never agree more.
Yeah, I would point out, I think there may be a distinction on how he's using the term and how you're using the term and how I might use the term. He's saying in that quote that the scientific knowledge of that is a spiritual experience, that is a spirituality, which is a legitimate position, but it's using the term differently. I think you're using it, and maybe I would use it the way you use it, is that that kind of spirituality is a different kind. That means there's something beyond that which is accessible to the scientific method or the physical existence, which is real, which many agree with and some don't. So
Yes.
I think we need to distinguish
Yeah.
the kind of
Yeah.
spirituality that he's
Yeah.
talking about, and you and I may be talking
And I
about.
think I do this in the book. I sort of say in a couple of cases that I'll go one step further than Carl Sagan might have.
Uh-huh.
And I think that I do in this case as well. I agree that he talks about science as a source of spirituality that you can have in the same way that people who go to um, church and would identify as religious have those sort of spiritual experiences in the church where they would consider it a house of God,
Or to an art museum or a concert. I mean, it's the
right?
same sort of
That a
a
scientist can experience that same.
a transcendence beyond yourself. Science can give you that, and I certainly agree with that. I
I
mean,
agree with
our
that.
whole our whole conversation is that. Uh,
Yes,
but
yes,
but the question is there something more?
right.
And
And that's where and Carl may not have said yes. That's where I say I believe the answer is
right,
yes.
yeah. And
And there's a lot.
I may be between you guys, but maybe I skew a little bit more to your side. So we
Well,
don't we don't have a lot of time left. But
yes.
tell me a little bit about Rising Stargirls. This is a unique endeavor that you've created that is really important for our culture in many different ways. So give us a sense of what that's about.
So I created Rising Stargirls because I saw a need. Um, Girls of color, and especially middle school girls of color, there's a sense when that age is reached that, and for all middle school girls, this is the case, that they start to become more focused on how they appear, their physical appearance, and how they're perceived, and they turn outward, and they're less concerned with how they think and feel about the world. And we've seen, of course, the numbers when it comes to women of color in my field, the field of astronomy. The numbers are very low, and that's changing to some degree in certain groups, but especially with African American women, the numbers are relatively static and have been since the late 1990s. So I wanted to find a way to involve middle school girls at this early age, because we know that girls they stop pursuing STEM fields long before college, even due to a lack of self-confidence and few role models who look like them. And I wanted them to develop a personal connection between who they are and the universe of which they are an integral part. And so I thought, how about I use my acting background and the creative arts in general, visual art, theater, and writing, to help these girls process what they're learning about the universe. And that's what we do. They're learning in these virtual workshops, and we're also going to be moving back to in person. And I'm excited that we just were awarded a 5-year grant from the Heising Simons Foundation to carry out our program, and that's just new news. To be able to we teach them, of course, what a constellation is, what different types of planets are, but they're always processing it through this personal lens. So they're writing poems about the stars and planets they learn about. They're creating their own artists' depictions of exoplanet surface environments, very much like NASA. With the creative arts, no one can tell these girls that the poem they wrote, the picture they draw is wrong. They can't get it wrong. And that's why I think this program is working. Of course, they're learning about the universe, but we're telling them that who they are as people, the family background they have, the conversation they had with their parents before they came into the workshop, all of that is relevant. We want them to bring their personal backgrounds into their study and practice of astronomy. And that's something that I think I had a perception that science didn't really care much about how I felt about doing the science. And that was a perception that I had because of the objectivity of science. And I now know that who I am as a person is quite integral to my ability to practice and study science. And that's that dissertation topic. It had to be personal to me. And when I saw that dual nature of ice
Mm.
originally, and I thought, this is like me with my astronomy and acting thing. That is what got me. That's what allowed me to be able to wake up every morning and want to work on something for 5 years, and so that's why we want to have that personal connection and start it early for the girls, because eventually, assuming they stay in astronomy, which that's the hope, that heavy math and physics will come in. And if they have that personal connection and grounding to what they're learning, they'll be less likely to abandon it when things get difficult.
Yeah, that's really wonderful, and we all support that. Finally, I read one thing that you said, which struck me very personally, and for this, I need you to be my teacher, because I've read that you are dedicated to rest as a daily practice and working restfully and less and more efficiently. And if there's any help that I need, it is that.
That made me so happy that you brought this up, Robert. I hope you saw my face beamed. This is like the next phase for me, and hopefully you'll be hearing a lot more about it in the future. Um, I've begun a rest practice. So, I was at the St. Louis Science Center recently giving a talk, and that talk had slides, and I projected a picture of a hare, a rabbit, and I was like, this was my personal mascot, and then it dissolved into a picture of a tortoise, a turtle, and I was like, this is my new personal mascot. The drive, the ambition, the hard work is certainly productive. And I have seen the benefits in my career of adopting that kind of a philosophy. I've also seen the toll that it's taken, both physically and in some cases mentally for me. And so I have had to slow down. And achieving tenure as a professor has allowed me to take that pause and determine what I want the next phase of my career to be, because no one is going to tell me, you got tenure, take a load off. Like, if anything, the expectation is to do more.
Sure.
And yet that's a choice that I get to make. And I have the freedom and the fortune to be able to make that choice consciously. I still get my work done. But in a lot of cases, it happens on a slower time scale than I'm used to. And there's a bit of discomfort in that because I've been pushing so hard for so long. However, I'm seeing the benefits. I talk a lot about how it's important to really turn inward more. I turned outward for a long time, as all of you will see and read in the book. But it's really by turning inward that I find the true answers to everything really about my life. What I want, what I would do if I didn't have to worry about X, Y, Z. What do I need to hear myself say? Like, all of those things I have to slow down to be able to do. Otherwise, it's very easy for me to just be on autopilot and do what is expected and busy, busy, busy. But I've looked into things like yoga nidra, which is basically like yoga. It's called yogic sleep.
Mm.
So it's not like you're doing a downward dog and chaturanga. It's like laying down and listening to a sort of guided meditation and scan through the body.
Mm.
And I do these for like between 10 and 45 minutes almost every day. And it is like having taken a deep nap. And often ideas will come to me. Again, when my mind is resting, that often is when creative ideas and inspiration arises. So I'm going to keep doing it because it's working for me.
Is Om your mantra? It's
I mentioned in the book too that loving when I started doing traditional yoga, it was like I would do the ohms, and I'm like, that's in my name. I had that
Yeah.
feeling of
So I think
connection.
that's important. In my case, I need to do more of that. The way I do it is I play intense table tennis, which with really good coaches, and they make me run a lot, and it's totally engaging to where it's like a transcendental meditation because nothing else can get in. So I think we all need to find our own ways to do it. But for those of us who are so driven, your approach to rest, I think, is really an important part of what it takes to be human. So thank you for that. Thank you for the personal revelations and discussions of your whole life, because I think that's a great source for many of us in different ways, and certainly for gender and race in particular, but for all human beings. So Many thanks, Aomawa, for a terrific book, Life on Other Planets, a memoir of finding my place in the universe. You have found your place, and you're helping all of us to find our place. So thank you very much. Viewers can watch hundreds of videos on cosmology and astrobiology on the Closer to Truth website and the Closer to Truth YouTube channel. Thank you, everyone, for watching. Thank you, Aomawa, for our wonderful conversation.
Thank you so much, Robert. I really enjoyed being here.
Thank you for watching. If you like this video, please like and comment below. You can support Closer to Truth by subscribing.